Hello students, good morning. We'll study today the speed of sound in different media and the speed of sound in solids, liquid and gases. See this first picture. From this picture, what are you understanding? Here, this hammer is struck on this metal sheet, and when it is seen from a distance, we can see first the sparking comes out, and then after we can hear the sound, the striking sound. So that this means what? This means that the speed of the sound is less as compared to the speed of that sparking or that light. Okay, so see the first line here. The sound can propagate only in the material medium, that means in liquid, in air, in water. Okay, so here the medium must be elastic. This is one of the property that we have studied earlier. Okay, the mediums must be elastic for the better propagation of sound. Okay, so here the factors on which the velocity of sound wave v depends are elasticity of the medium. This is one of the factor, and this elasticity can be determined by the Young's modulus of elasticity E of the medium, correct. And it is also depend on another factor, that is the density of the medium. So overall we can write this V is equal to square root of E divided by rho. Okay, here E is the Young's modulus of elasticity. Okay, and rho is the density. So this gives the speed of sound. Now see the next pic. In this next page, first we will see what is the view of Newton. Okay, according to Newton, when sound travels in a gas, then it is an isothermal change. So what is the meaning of isothermal change? Here the temperature of the gas does not changes. Okay, and if the temperature is about to change, then what happened? Some amount of heat is released from the gas. Then what happened? The temperature remains same. If the temperature is to be reduced, then some amount of heat is added. Okay, so in this way there is some exchange of heat or amount of heat added or removed, but the temperature remained constant. So this type of change is called isothermal change. So here for this isothermal change, the elasticity, that means the Young's modulus of elasticity E is equal to the pressure P of that gas, correct. At normal temperature, the pressure is given as 1.01 into 10 to the power 5 Newton per meter square, and the density is given, density of the gas or air is given as 1.293 kilometer kg per meter cube, correct. Now if we substitute all those value in this particular relation, because we all know this E equals to P, so this V equal to P divided by rho, and for P we can put all the value. P we have, rho we have, correct. So if it is calculated, we'll get the value, we'll get the velocity 279, that is 279.5 meter per second. Okay, second, it is second per second, not second square. So 279.5 meter per second, and this is the experimental value, 330 meter per second. So what you see, the experimental value, this one is different from this calculated value. Okay, so later another scientist Laplace gives his condition, given his condition, and from according to Laplace, when sound travels in a gas, no exchange of heat for compression and rarefaction take place. So that means the temperature changes. Okay, the temperature of the gas changes as there is no any exchange of heat. That means see, when the sound is propagating, there is no any exchange of heat and the temperature changes. Okay, and this type of change is a just opposite kind of change as compared to isothermal change, and it is called adiabatic change, correct. And for the adiabatic change, we have elasticity E is equal to, that is Young's modulus, is equal to gamma into P. Okay, the gamma into pressure. So here gamma, what is gamma? Gamma is equal to Cp by Cv, that is the ratio of specific heat in constant pressure and the specific heat in constant volume, correct. Here Cp means the specific heat in constant pressure and Cv means specific heat in constant volume. Okay, so gamma is the ratio of Cp by Cp and Cv, and it is given 1.4. The value of gamma is 1.4, and for at the normal temperature we have the value of pressure and the value of density of air. So we can put all those values. We have also this part, this additional part, we can put this value also, and now we have velocity is equal to velocity, that is speed of sound is equal to square root of gamma into pressure divided by density. We can put all the value and see when it is calculated we will get 330.7 meter per second. Okay, so here this calculated value 330.7 is almost equal to the experimental value, that is 330 meter per second. So we all agreed to Laplace. So here the velocity is given as the square root of E by rho, Young's modulus of elasticity by rho. So that means what? If E is greater, that means if this elasticity is greater, generally for the solid elasticity is greater, that means solids are more elastic as compared to liquid or gases or any fluid. Okay, so for solid this E is greater and this velocity will be greater, correct? So the speed of sound is greatest in solid as compared to liquid and gas. And now if we compare with liquid and gases, the speed of sound is greater in liquid compared to gas, and speed of sound is least in gaseous medium. Okay, now here this part we can prove by this example. Here this one, suppose a rod, okay, a pipe, a long steel pipe, correct? So if it is a pipe, so that means it is a hollow pipe and inside the pipe air is present. Now suppose it is a long pipe, very long pipe, and when a sound is produced here, okay, a sound is produced here, then if we hear from this side, first we can hear two sound. Okay, here we can hear two sound. Why? Because the first sound comes with the steel, with the body of the steel, that is the first sound is traveled through the metal, that is through the solid, and we know that the speed of sound is faster in solid medium. So first we will hear the sound that comes from this body of the solid, and then later the second sound is heard. The second sound is also heard. That second sound comes out through the air medium at the middle of the hollow pipe. Okay, the air present here at the middle of the pipe that carries the sound, another sound. Okay, so we can hear two sound. So this proves that the sound can travel in different speed in different media. So in solid it has the speed it has greater speed as compared to in gas or liquid. Some other example we can also take, like suppose a train is coming, and if we put our ear near the train is very far, okay, now the train is very far, and if we put our ears on the rail, then we can detect the vibration, or we can detect the sound produced by the wheels of the train on the rail. Okay, even the rail is very far from the train is very far from us, correct? So here the sound is propagating through the body of the rail, the metallic rail. Okay, I'm talking about the rail. And then later, if the sound of the train, it comes later. Okay, because in air, through the air, the sound of the train is travel in a lesser speed as compared to in liquid. One more example we have. See here, the same example I have taken. If this is a big metallic plate or metallic sheet, big, very large, very long, and here it is stacked. So first we can hear the sound that travels through this metallic sheet, and then later the air around this air around this hammer, or at the upper part of this sheet, that carries the second sound. So here also we can hear two different sounds. Hope that all are you understanding this part. Okay, so simply this solid body carries the sound, and another second sound is carried by the air. Okay, the air around it. So that's why we can hear two different sounds. Okay, and for that we have to put our ear on this metal sheet. Okay, now see the factors affecting the speed of sound, and the first one is, see here, suppose speed of sound in a gas kept in a pressure P. Okay, so here the P remains unchanged, that means the elasticity E remains unchanged for a gas, because P is the pressure which is maintained constant. Okay, so here suppose we are changing the gas, and with the change in gas the density is changing. Okay, suppose we are taking oxygen and we are replacing the oxygen with hydrogen, so that the density will change. So here with the change in density, as pressure is constant and this gamma is also a constant. Okay, so this overall part, the numerator, is a constant, so you can directly say that this velocity is inversely proportional to the square root of the density. Correct? If the density changes, the velocity, the speed of sound also changes. But with the decreasing, see here, the speed of sound is inversely proportional to the square root of density. So that means lesser the density, greater the sound. Okay, like in the hydrogen gas, the density is less. Okay, so that if the density is less for the hydrogen gas, then the sound is greater, the speed of sound is greater in hydrogen gas. We can prove this part. See, here we have the velocity of sound in hydrogen and velocity of sound in oxygen. Those two are divided, and see, square root of density of oxygen divided by square root of density of hydrogen gas. Okay, so here we know that the density of hydrogen gas is 1, and if it is 1, that means the density of oxygen gas is 16 times as compared to that of hydrogen gas. Okay, so if we put like that, square root of 16 for the oxygen gas and square root of 1 for the hydrogen gas, then we will get 1 by 4. Correct? So here we can say that the velocity of sound in hydrogen gas, okay, which is lesser in density, is greater. So for every less dense gas, the speed of sound will be greater. Correct? And if the density is greater, then the speed of sound is through this medium is lesser. Now see the next point, temperature. It is another factor that affect the speed of sound. Okay, so temperature of a gas is directly affect the density. Okay, it is directly affect the density. Why? Because increase in temperature, it is directly not, it is inversely affect the density. Okay, so here increase in temperature decreases the density. Correct? Why? Because temperature causes expansion of the gas, and if the gas is expanding, so the volume is also expanding. If the volume is expanding, then what happened? Then the density will reduce. Okay, because volume is the denominator. Density means mass per unit volume. Okay, mass divided by volume, and if the volume is increasing with the temperature, with increasing temperature, then obviously the density will decrease. So here, if the density, see, I will read this line once again, temperature of the gas is inversely affect the density. Okay, increase in temperature decreases the density of the medium of the gas, and then the speed of sound is found greater with a less density. So here, as from the previous part, we all know that V is inversely proportional to square root of density. So we can say that V is now directly proportional to square root of temperature, as because this temperature and this density are inversely proportional. Okay, so we can take V is directly proportional to square root of temperature. So see, this is the second condition, the second factor on which the speed of sound depending or affected. Speed of sound is directly proportional to the square root of the temperature of the gas. Okay, so here suppose speed of sound is increases, so with increase in temperature per degree Celsius, or per degree Celsius, the speed is increased by 0.16 meter per second. Okay, see, let me read it once again. Speed of sound increases with increase in temperature. Okay, and for each degree of Celsius, for the increase of each degree Celsius, the speed is increased by 1.6 into 10 to the power 0.6 meter per second square. Okay, so here suppose the temperature increase from a particular temperature to a final temperature. So from initial to final temperature. So here whatever the change in whatever the new velocity, it is velocity or speed of sound at the temperature T, the final temperature, is equal to whatever the speed at initially, okay, at the initial condition, and then after it is added with 1.61 into T, correct, as because for each degree this 0.61 meter per second is the increase in velocity for each degree. Okay, so here T degree is the change, correct, so from 0 to T. So here the Vt, that means the temperature, the velocity, the speed of sound at the temperature T is equal to whatever the velocity at 0 degree added to plus 0.61 into T. Okay, here T means the change in temperature, that means T minus 0, the increase in temperature, correct. Now see the fourth factor, yeah, this one is the third factor, the effect of humidity. Density of water vapor is less than the density of dry air, okay, and it is given that it is 5 by 8 times the density of dry air. Okay, so always the water vapor has less density, which is 5 by 8 times the density of dry air. And suppose, see from this picture, this is dry air and this is water vapor. From this picture you can understand that this one is more denser as compared to this water vapor. And suppose if we consider about a humid air, so this humidity should be added with this dry air, okay, and now this is the air, humid air, and see you can easily understand this humid air has lesser density as compared to this dry air. Okay, so we can say that humidity in air reduces the density. As humidity added to, as water vapor added to air, that means the air become humid, so it becomes, it reduces its density. So it is written here, the density of humid air is less than the density of dry air. And finally the speed of sound in air increases with the increase in humidity of the air, as because if you all know that if the density decreases then speed increases. So here see density of humid air is less as compared to the dry air, so here for this the density is less, so that means the speed is greater, and here for that the density is greater, so the speed is less. So as the air become humid, its density reduces and its speed increases. So the final statement is that the speed of sound in air increases with the increase in humidity, correct, because increase in humidity reduces the density. Now see the next, this is the fourth factor, effect of direction of wind. Okay, so here it is very simple that when the wind blow, so when the wind is blowing, then speed of sound is added with the speed of wind when both travels along the same direction. See, if this is the speed of sound and if this is the speed of wind, then those are added. And if suppose the speed of wind is opposite to the speed of sound, so speed of wind is subtracted from the speed of sound. Okay, yeah, this one is sound. Okay, speed of sound, not the wind is cat. So when sound is propagates or traveling opposite to the direction of wind, their velocities, their speeds are to be subtracted. So this is the velocity of sound, it is subtracted from, it is subtracted to with the, that means the velocity of wind is subtracted from the velocity of sound, correct. Now the factors that not affecting the sound, the speed of sound. So let's see, the first one is, see here, effect of pressure. So let's see here, the speed of sound in a gas of density rho and pressure P. So here this is the speed that we know the formula, many times we have visited this formula. So the effect of pressure, what is the effect of pressure? Suppose we are considering that the pressure increases the volume. Okay, suppose we are increasing the pressure, so this pressure of a particular gas, we are increasing the pressure, so this pressure, this increase in pressure decreases the volume. Okay, and if the volume is decreases, volume means mass divided by volume, okay, sorry, density means mass by volume. Okay, so when the pressure increases, that volume decreases. and the density, that is m by v, increases, because this v which is denominator is decreasing now, so the density increases. So with the increase in pressure, the density increase, correct? So if the density increase, then what happened? The pressure is increasing. So here you can see the pressure as well as the density both are increasing. Okay, so here at what rate the pressure is increasing, at the same rate the density is also increasing. So this overall ratio will remains unchanged. So this is written here, p by rho remains unchanged for a particular gas. Okay, when the gas is kept, yeah, it is written here, if any gas is kept under high pressure. Okay, so the high pressure, higher the pressure is higher the density. Okay, higher the density, that means high pressure reduces the volume, and if the volume reduces, the density is greater. So this p by rho remains unchanged. So here, if any gas kept under high pressure, the speed of sound through the gas remains the same, remains unchanged, correct? Now see the next factor that will not affect the speed of sound, that is the amplitude of sound wave. And another one is the wave or frequency, the wavelength of or frequency of wave. This is also does not affect the speed of sound. That means the speed of sound does not depend on wavelength or frequency of the wave, and it is also does not depend on, it is also does not depend on the amplitude of the wave, correct? So see here, we have compared the speed of sound and speed of light. So see, the first, for the light, the maximum speed is in vacuum. Okay, whereas sound cannot propagate in vacuum. The light, the speed of light is 3 into 10 to the power meter per second in air, whereas in sound it is 330 meter per second. Okay, very less, very less. Here the speed of light is reduces or less in water, okay, in the optically denser medium, whereas speed of sound in liquid, that is in water, it is greater as compared to that of liquid, correct? So here the light is a transverse EM wave. EM wave means electromagnetic wave, transverse nature of electromagnetic wave, whereas the sound waves are longitudinal, that you all know, longitudinal mechanical waves. So one of the consequence that the speed of sound and speed of light, and speed of sound is lesser as compared to speed of. First example that we have taken, when the hammer is struck on the metal sheet and the sparking comes out. Okay, here the lightning and thundering is one of the example. Whenever the lightning occurs, first we see the sparking and then later we can hear the thundering sound. Okay, so that means firstly the, but remember that lightning and thundering both occurs at the same time. Okay, but due to this greater speed of light, we can see the sparking of light first, then after, as because speed of sound is very less as compared to that of light, so later we can hear the sound, that is the thundering sound. Now the experiment to measure the speed of sound, okay, to determine the speed of sound. Here we have, see this one you can do, this two places you can choose, okay, the high altitudes, and in between them the distance is 1 kilometer. Then after, suppose one is fired a gun from here, and then with the name A. Okay, so the when the gun is fired, the time is noted by the stopwatch, by using the stopwatch, and it is noted as T1. Okay, when this A fired a gun, when this A fired a gun, then the stopwatch is to be on. Okay, and when the sound is listened, then the stopwatch to pressed close. Okay, and whatever the duration can be detected, and it is marked as T1. Okay, it has the value T1. The same time, the same thing for B also. B will fire a gun, so when it fires a gun, so when the light comes, then this A ons the stopwatch, and then after, when the sound is heard, then it stop the stopwatch. Okay, and whatever the duration, measured. So t2 is the duration. Now the average time we can t equals to t1 plus t2 divided by 2, and then after we have time, we have the distance, that is 1 kilometer. So velocity is equal to, the speed is equal to distance divided by time. Okay, so in this way we can calculate, or we can determine the speed of sound. So thank you class.